All right, so yesterday we finished off looking at an example of how to do a bottom-up heap construction. Let's just remind ourselves why this is important. We began by discussing a new ADT last week called a priority queue, where instead of putting things in and removing them arbitrarily or inserting and removing them based on their position within a list, as we did in our positional list, our queue, our stack, instead now we looked at arbitrary insertions. However, we want to be able to remove things in order of priority. And so for our priority queue, the two methods or the two main methods are insert and remove min. We then looked at different ways that we could store a priority queue and how that influenced the runtime of our methods. Actually, before we did that, we saw that we can sort a list using a priority queue by inserting all the elements of the list into that priority queue and then removing them one by one using our remove min method. So from there, we looked at different implementations of priority queue. We saw that we can store it in a sorted list or an unsorted list. In both of those cases, inserting in elements and then removing them using remove min n times would run in quadratic time, order n squared time. We then introduced a new ADT, our heap. We said that it's a binary tree, but it also has some properties. One of the most important ones being that it has this heap order property. We looked at how we can do insertions and removals from that heap, and that if we're storing a priority queue inside this heap, we can then do insertions and removals in order n log n time, and we call that heap sort. If we're just sorting using a priority queue, we call that PQ sort or priority queue sort. If that sort is stored in a heap, then that becomes heap sort. We saw that the runtime is pretty good as our best sorting methods to date, like quicksort and merge sort. And then we looked at the fact that we can actually speed up the first part of that process of inserting n elements. Instead of having n successive inserts into this heap, storing our priority queue, we can instead do a bottom-up heap construction. All right, so we ended there, and as I promised, we're going to look at a couple more examples, and we'll go from there. Someone asked, where can I submit a sick note in case I'm not able to write? Please go look at Eve. There's a notice about that, the SSA, and a link to the form where you can submit that. You have to submit an application using that form and attach or upload your supporting documentation. All right, please don't ask questions here on Discord that make it clear that you're not paying attention or going to Eve. I keep seeing questions on Discord that clearly show that you're not coming to class. So please, before you ask questions, go look at the notices on Eve, and of course, listen to the classes if you haven't seen, if you weren't at the live lessons. So as promised, let us go look at, let's say, 2 more examples. That should make us very comfortable. Okay, so let's go to our whiteboard. It says I might have some audio issues. Please, if there's an issue, I see that it is picking up my audio, but it's warning me that there may be an audio issue. If there is, just please type into the chat. I'll see if I can change that as necessary. Okay, this whiteboard is really not being my friend here. For some reason, when I try to paste these numbers that I've copied here, it is unhappy. Okay, that's refusing to work, so I'm gonna have to write out the numbers before we get started. All right, which is just fine. So let's say that we had this list of numbers and we want to insert them into a heap. I have 5, 6, 1, 10, 7, 56, 43, 23, 15, 9, 8, 32, 2, 35, 36. So as we agreed, I could actually insert these into a heap one by one. What is our method for inserting? We keep track of the last node. So I could insert 5 here into the empty heap. Then the last node that we're keeping track of there would be the left child of uh, that root. So I'd use some variable to keep track of that. I can then insert that 5 there, sorry, the 6 there. Then we set our method for finding the next uh, position or the next node to insert our new element would be to go up until we get to a left child and then go to the sibling of that child and go left until we reach a leaf. So here we already add a left child. You can just check, is this node equal to its parent's left? And so we can go to its sibling, and its sibling indeed does not exist. So we're able to put in 1 over there. Right, and we can continue in this fashion to do this. However, we said that it'd be better for us to simply do a bottom-up heap construction. Right, this would take n log n time. We can do it in order n time by doing this bottom-up heap construction. So we agreed yesterday that a good way to determine how many levels we need is to actually look at how many we would need to make our root, then our root's children, then those children's children, and so forth. So here I need that for my root, that's at depth 0. I need these 2 for the children of my root, that's at depth 1. I need 4 more at depth 2, so my third level. I need 8, let's see, 1, 2, 3, 4, 5, 6, 7, 8. I happen to have 8 there. So this would be at the 4th level or depth 3. So now I understand how I can split this up to be able to create my heaps that I continually combine using an extra node. So let's start with these heaps that really just have a single node in each. So they'll definitely be valid heaps. Perhaps just write it first, then circle. And I have 1, I have 10, I have 7, 56, 43, and 23. All right, then for each of those, I need another element to make the root of my new heap. So I start taking elements as necessary or as needed. I'll have here 15. That becomes the root, and we have the 2 existing heaps becoming rooted at the left and right child of this new root. Then I'll use 9 over here, then 8 over here, and 32 over there. All right, but are these valid heaps? Well, we have to check first that our heap order property has been preserved. And I see that actually none of these do that. So I have to do some switches. So I'll say, all right, 15 should switch with its smallest child, 5, 9 with its smallest child, 1, 8 with its smallest child, 7, and 32 with its smallest child, 25. So I would stop, that would be like the first, that's really as many steps as I can combine in a single figure. So I'll then start drawing again and showing what my new heaps would look like now. I'll have 15 as the left child here, 6 as the right child there, and 5, which is now moved to be the parent. I then have 9 as the left child here. Oh, it's a 23, thank you very much. I'll take note of that. Right. Oh, and that's actually a mistake that comes up a lot, which is interesting. So make sure you can read your own handwriting. 9 is the left child, 10, and for interest's sake, you would lose a mark, but then we carry the error from there. Then 8 and 56 and 7. Then I've switched that 32 with the 23, so 43 remains the left child, 32 becomes the right child, and we have 23 as the root of this new heap. So I now have 4 heaps. I want to combine those again. I need more keys. I take 2 as the next key. That becomes the new root of that heap. I then have 35 on this side, and it becomes the new root of that heap. Now I have to do a down heap to make sure that the heap order property is preserved. Here I see that 2 is actually smaller than 1, or larger than one of its children. So I'll swap 2 with 1. On this side, it's actually bigger than both its children. I'll swap with that. And each time check is, would the heap property be preserved if I did that switch? Not quite. I would actually need to do another switch. Perhaps you want to do this in 2 images actually. So I'm saving a little bit of time. But make sure that if you do one, you can keep track of what you're doing. Because not that 35 is going to go down there and then 8 goes to the top. It's that 35 first gets switched to 7. Then 35 gets switched with 8. All right. Now let's see. Can I zoom out a bit here so I can see it better? My whiteboard for some reason is being rather disagreeable. All right. So let me rather just do this. Obviously, you should not do this. For some reason, my whiteboard doesn't want to zoom out. All right, and so I'm left with 7, 8, and 35 there. I then take the last number that I have, which is 36. That will become the new root of this final heap. Again, I have to check, do I have my heap property preserved? I may have to do a down heap. I am going to end up having to do a down heap. 36 will switch with 1. Still not right. 36 will switch with 2. Still not right. 36 will switch with 9. So I will redraw the final state so we're on the same page. It's 15. I have 6 here. I have 5 here. Then some things have changed here. I end up with 2 over there. I end up with 9 over here. I end up with that 36 over there. Still have 10 over there. My new root is now 1. The other side of it remained unchanged. I had a 7 over there. Its left child is 8. Getting squished. Whose left child is 35, and the right child is 56. The right child of that 7 is 23. 43 was its left child, and 32 its right child. All right, so that'll be the final state of our heap. You get, I think this is for about 10 marks. So you get a mark for each correct heap state that you depict. So for that first line, okay, I'll answer that question now. For this first series of heaps, you would get a mark for that. You get a mark for inserting. You get a mark for the down heap. Again, mark for inserting. No, you've already said it. Mark for inserting, mark for the down heap, mark for inserting, mark for the down heap. All right, so that's how your marks would be. And we usually have a rather complex or rather involved down heap for the last one, so you usually get about 2 marks for that. Or 3, actually, I think it was in this case. 1 to 3, 1 to 3, 1 to 3. Yeah, I think it was 3. That'll get you a 10. All right, there was a question. Let me look at the chat. What happens if you don't have the max node in the list you're given for each level? For example, level 3, you're given 9 elements instead of 8 elements. Well, let's do it. Okay, so I'll have to just delete everything. Unfortunately, there doesn't seem to be the option to simply erase one thing. But let's look at an example. And this time I'll zoom in first so that I have a little more room. And let's see. So let's say we were given not something that's a number that's equal to, yes, that's not equal to, you can't see, I believe you can change your own zoom level. I haven't written anything yet. What I'm saying is if I had, oh, that looks terrible. All right. If I had something like, it really does not want to scale up or scale down, rather that writing size. Okay, so if I had, let's say, 2, 3, I'm very lazy, 4, 10, should actually have some smaller ones as well, so we have to do something. 5, let's see, 1, 2, 3, 4, 5, 6, 7. I know that this is actually equal to 2 to the power, what, 3 minus 1, so that would work nicely. But let's say we had another 30 here, and we had a 6 there. All right, so now I'm between 7 and 15. It's not going to work out quite as nice. Again, I'll say, all right, I'll need this for, I'll need this for my first level, so depth 0. I'll need these two for my second level, depth 1. I'll need 1, 2, 3, 4 for that depth of 2. And these two have to be at depth 3, right? They simply have to be by themselves there. So I'll end up with 2 here, 3 there. Then I start using the others that I required. 4 there, 10, 1, 5. This will need to do a switch to make sure the heap property is preserved, heap order property. And then I can start pulling in the others that I need. 8 and 30. Here I'll have to switch these. And here I will have to actually switch this and that. Now that's my smallness, this and that. Let's redraw that. End up with 8 here. Its children are, no, I'm not even doing what I said I'd do. 2 there, whose left child will then be 3, then 8 there, and then 4 there. Then over here I have still my 10. Over there I have the 1 has been switched with the 30, and 5 is still the right child. No, you can't draw everything first and start switching. You end up with something different. All right, ideally, each time you change something, you should redraw it. Then let's see, we have our 6 there. Not even ideally, you should, otherwise you will get the wrong answer. If I'm doing the down heap, I can get away with doing this because it's easier to keep track. But if you're doing more than that, you shouldn't. And in fact, if you just draw everything in the heap, then do the down heap, you will definitely get the incorrect thing. All right, so here I can keep track of the fact that I'm switching 1 with 6, 1 with 6. Then I switch 6 with 5. And so then I could redraw my last one. All right, so that's what we do when we don't have a number that is, 2 to the power some number minus 1. So if it should be something like that, then it'll be the easiest, but if it's not, we can still work it out. We'll just start from the right we agreed yesterday and see how many we need for each level. Whatever's left over will go to a new level. And as we agreed, we fill from the left, right? Because external nodes is to the left of internals or to the right of internal nodes, which means that we have to fill up from the left. Okay. So that is good. Do we require one more example? Yes or no? Nope. All right. Okay, so I have one no and 2 yeses. So I'll certainly look at one more example. Okay, let's see here. If I were to trick you, what it would look like? It would look like having what we just saw now. We don't have a number of nodes that fits nicely into a tree because then you actually have to choose where to put them. And to make it a valid heap, you have to put them on the left. If you were to put them on the right, well, then right away, you don't get marks from that step because it's not a valid heap. And with a valid heap, or rather the heap properties are not just a heap order property, it's also that external nodes need to be on the right of the internal nodes. So if you do something like this at a particular level, and you have this one having kids there, and perhaps that one as well, then I have here at one level the external nodes being to the left of the internal nodes, and that's all we agreed. So that would not be correct. Right. So let's see, I'll take 10, 3, 5, 7. You should show the arrows. That's the only way that you indicate that the down heap is happening. If you do everything step by step, then that's fine. We can see it. But if you're doing, um, down heap all the way down to a leaf, then you should draw those, or we can't see. Or yeah, just whatever makes it easier for your marker to be able to see what you're doing helps, because then if there's a single error, we note that, we'll circle that node in red, and you lose just a single mark there, and then we know from that point we don't follow the memo, we follow your logic. And as I said, most of the things you're dealing with now, besides the skip list, are different types of self-balancing trees. So you have a lot of these where you're drawing the different states of the tree, and mistakes happen. So rather indicate exactly what you're doing, so that if there's a mistake, we note it and carry that mistake into the next steps. And some of these for as much as 15 or 20 marks. So it would be really bad to lose all those marks. All right, so as we agreed, that would be my root. I then need 2 for its children. I need 4 for the next one, and that'll work. Right, so I will start with using the bottommost ones. Okay, so that's already correct. You get a mark for that because those are 8 valid heaps. Then you for the last one, we're happy. So I'll do this, the next state next to it. 10, 33, then 15 switch to 5, and I still have 7 on the right. Then 24 has been switched to 13, I still have 20 on the left. And I leave the rightmost heap as it was. Okay, so then I want to use the next 2 elements to combine these heaps. Just scratch that out so we don't confuse ourselves. Okay, then for each of them I check. I see that the heap order property is not preserved here. I need to switch 9 with the smallest child, and that is enough. I now reach a node where its children are larger than it, or the keys of the children are larger than it. And then on the right, I have to switch 5 with its smallest child. So if 5 were there and 1 were there, I would still have to do it again. I'd end up with a 2 there and 5 there. I will redraw that as I should. I will then have 10, 30, 9, since 9 was switched to 3, and 3 there. The right child stays the same. Its children again stay the same. Then I have the other, I need to switch 5 with 1, and then again with 2. I end up with the 5 over there. The left child of the 2 is 26, I believe. Okay. If it's for marks, I'll definitely go and double check that to make sure. 13, 20, let's make this clear, that's 6, and 24. All right, I have one element left. I make that my new root, and I have there my final heap, but it is not a valid heap. Heap order property has to be preserved. This one's nice and easy. I'll actually be going along this right side the entire time. So let me quickly draw what I should have there. I should have 10, 30, 15, 7, 20, 24, 26. I should end up with the 12 there. And then this remains 9 is the root there. Well, that's the parent. 5 is the parent there. Third. What do I do there? 5 is the parent there. 13 is the parent there. And we said that now the 5 swapped with the 12. All right, if you have a hand, you can just type the question in the chat there and I'll address it afterwards. Then over here, this one remained the exact same, but I could have redrawn that entirely. I had my 2 swap with the 12 on its way down. I end up with 1 there. Right, and there you end up with your valid heap that was created using a bottom-up heap construction. We saw that we just need to do down heaps each time that we are combining heaps, not each time we're inserting an individual node. And that's how we end up with order in time construction of a heap rather than n log n, which would be what we get when we do our usual, or rather if we just did n inserts into that. All right, I will. Now, there's not that much time left, so I'm not going to attempt to cover the entire section on adaptable priority queues, but rather introduce the idea. Prof. Van Ha has already stated that he will start from there. So he will cover it from the beginning, but it does not hurt. In fact, it will assist you to just know what is being discussed before we start on that next term. So I believe we're looking at the different ways of storing our heaps, then merging our heaps. We looked at how we do that programmatically, and we ended up with the analysis. Okay, hold on. There's a question. If we have the case where we have the same number, need to allow a number to repeat itself? Yes, okay. We can have that, and it's important that we all use the same convention. All right. So I'm going to say now, if it is equal, then go to the left. Actually, we haven't gotten to that stage yet where we need to agree on something like that. When you get to binary search trees and that, you will have to agree on that. Right now, as you're inserting, yes, you can have the same number, and our agreement was that you stop when it is valid. So when you get to a node, the children are not smaller than the parent, then you can stop. So let's say we put in that one, okay, bigger number. We put in that 12, and as we're going down the right there, we saw that its children were perhaps 12 and 24. We would have stopped right there. All right. With some of the other trees that we work with, you will actually have to decide which branch you go down, the left or the right. But we will agree on a convention and stick to that. All right. So I just want to introduce the idea of an adaptive priority queue. So for a priority queue, we said it has 2 methods, this insert and remove min, and it does what we require it to do. Question, are we doing min heaps or can we also be asked to rearrange a max heap? No. Those are really the same. It's simply which convention you follow, whether a high number implies a high priority or a low number. We go with the low convention, so it'll always be a min heap. We don't even call it that. When we do a heap, it is assumed to be a min heap. Granted, if you look online, you're not going to get as much assistance with that as you do with the max ones, but that is just fine. All right, so thus far we've looked at priority queues where we are inserting and removing min. However, what happens when one of the entries in our priority queue changes one of its properties? So we said that our entries were now key value pairs. The key which has to be able to be compared to other keys. So we have this order, and the one with the highest priority can be removed when we say remove min. However, that could change. And the text example that's given is, well, when we're looking at the example of people who are on standby to join a flight, and the person with the highest priority will be given a seat on that flight if one opens up. Well, what happens if one of the entries there has its key change? So let's say you are flying first class, but you're not a frequent flyer, or you're flying first class and you are a frequent flyer member, but you didn't have your card with you. So your priority was determined simply using your class and perhaps what time you had initially booked. However, you then find your card. So you have the number now. So we can add that into the calculation of your key, which determines your priority. And so we have to change it. Now, can we do that with our current priority queue? No, not unless we know where your entry is in the heap. And we only keep track of two nodes, the root and the next one. So how do we, even knowing what your key and your value are, how do we actually find where you are in the heap so that we can be able to change those properties? And the truth is that we can't with our priority queue as it is. We only do inserts and removals. Also, what if your name was spelled incorrectly? We now need to change the value of that entry, not the key. Again, we need to be able to get into a particular entry within our heap, or let's be more general, within our priority queue to be able to change it, regardless of what that priority queue is stored in, right? Linked list, array, heap, whatever it may be. And so we're gonna now introduce some new behavior, and this is going to create a new ADT called an adaptable priority queue. There's one last one that I didn't quite talk about, remove an entry. So what if someone decides, I don't want to be on this flight anymore, and it may not be the person who had the highest priority. So we need again to have some way of removing that person from the queue. Think about something you may have actually experienced. Let's say you're at home affairs or you're at a bank or the pharmacy. You've taken that slip of paper that says what your priority is in that queue, but then you decide, okay, I don't want to be here. I've run out of time. I have to leave the bank or the pharmacy. If you just leave, then when you're the next one at the highest priority, they'll call your number again and again and again, and eventually take you off that queue. Granted, with the queue, the priority is just the order that they arrived in, but they're still priorities. So instead, what you should do, oh, and in fact, some banks do use more complex ones. It depends on your order of arrival and what you're there to do. Pick up a card, open an account, whatever it may be. So what you should do is you should go to whoever's assisting with that queue and say, I actually want you to remove me from it. So we'd also need this ability to remove an entry from a priority queue. And this leads to these three new behaviors of an adaptable priority queue: removing an entry, replacing the key of an entry, and replacing the value at an entry. All right, that's all the time we have, so I'm going to stop there, but I just want you to note that we actually have a problem. We cannot, even if we know what the entry is, even if we have the reference to an entry, that does not mean we have the reference to its position within the priority queue. What do I mean? Let's say we're using that heap structure, so we have these linked nodes. Each node stores a reference to an entry, a key value pair, a reference to its parent, and a reference to children if it has them. If I have that reference to the entry, that does not mean I have a reference to the node that it's stored within, that position, right? And so I have to have some way to actually, while tracking an entry, so you tell me, okay, I'm this person, I want to be removed from the queue. I have to have some way of knowing where in that priority queue you exist. Let's say it was stored within an array. Given your index, I can index into the array and access the entry that represents you. However, just having your entry doesn't mean I know what your index is. And I need your index to be able to find your parent and your children so that I can do either down heaps or up heaps, depending on what the change in your key has been. Similarly, in the node structure, if you change your key, then we still have to keep the heap order property. We may need to down heap or up heap you, depending on whether your key is now too large or too small for where it is. So we actually need some way to, given a reference to an entry, access its parent and its children of that position in our node structure. So what we'll find is that even our entries are not quite enough. We're going to have some way of knowing where an entry is, and that brings up this idea of a location-aware entry, so that each entry stores a reference to its location. And if this was in an array, each entry would then store its own, oh, I seem to have gone too far. Each entry would then store its particular index. All right. But as I said, Prof. Van Gaal will start there again and pick up from there. But it will help if you understand why we need an adaptive priority queue, because people can leave or change their properties. And that leaving may not be the one who has the maximum priority, or rather the highest priority. And we need some way then to know, given the reference to an entry, where is it actually in that priority queue, so that we can do some of that up heap, down heap that we need to be able to do for our priority queue to still work correctly when it's stored either in a list structure or in an array, or using that heap structure of our linked nodes. All right, so we'll stop there. We are having a prac tomorrow, so please arrive on time for the prac lecture. And then you'll be done for the semester. We wish you all a good, restful mid-semester vacation. But please don't just leave your projects. Those you should still be working on so that you aren't pressed for time in the next term. Someone asks, with regard to a blockchain, what is meant by proof of work? Okay, and actually this is an issue that we saw with a lot of the submissions, that you understood what we did in our prac when I did that hash list, that by hashing, what did we look at? We looked at if you actually hash all the pieces of data and use that, take the hash of that hash and so forth. All right, so we understand that if I have a list where each entry contains a hash of itself and the hash of the previous entry, then each successive entry would have to be changed if I was to change a single entry, right? So that doesn't make the list unalterable, but it makes it difficult to alter. All right, but that does not tell us, that each block that is added, each new block is actually valid. And what I mean by valid is, does it represent a transaction that actually happened, right? So we have to have some way of doing two things, although we can do them both at once. We have to incentivize our nodes within our blockchain to only do the right work, so to try and add only valid nodes, and incentivize the other ones to check that work thoroughly. So if we look at the example of what Bitcoin does, is that it uses mining. So each node, all the nodes actually, compete to create the new block, because to create a block, you need to actually solve a complex cryptographic, how can I say, problem. You have to try and find let's see, you have to try and make sure, yes, you have to try and make sure that the hash of the particular block starts with a series of zeros. How do we do that? You add something called a nonce, and you can change that to change the hash. However, a hash is a one-way function. The only way to get a particular output given different inputs is to test many, many, many inputs. So you're actually doing a lot of work. Would you want to do that work unnecessarily? No. So In order for you to do that work, you're rewarded with some coin, some Bitcoin. And then once you have, let's say you finished that solution first, so you get to add the new block. Everybody that you're competing with to add that new block then switches from trying to add a new block because they lost to actually verifying that yours is correct. They check your work to check that it's correct. If you didn't do the correct work, then they instead get your coins instead of you. So it's a system of punishment and reward that incentivizes people to do the correct work and others to thoroughly check that that work was done. So that's proof of work. It's a way of reaching consensus that uses a system of punishment and reward. Not all of them use that. Others use proof of stake, where instead it's your stake in this network that determines whether you are allowed to add the next block. And so it depends on who has had the coins, Potomac coins, the longest. You could think about which nodes have been running the longest. There are different ways to determine stake. But really, it's just an example of a consensus algorithm, a way of reaching consensus in a network without having a trusted independent party. And how they do that, they have a system of punishment and reward. All right, I'll leave it there. Next term online teaching, yes, the DVC did decide that now it's going to be the entire first semester at least. If your project is rejected, what's the next step? You have to make the necessary changes to make sure that it adheres to the requirements of the mini project. That means look at the feedback you got, go and watch that video that Prof. Van der Haar put on Blackboard. It shows you exactly what is required, and he looks at some examples of consensus algorithms. So go and take a look at that. Whatever is missing, based on the feedback and your viewing of that video, you need to change it to make sure that there is enough. You don't have to resubmit, right? The idea is that we gave you some feedback on, okay, you've either done enough or not yet, and you need to now go and see what's missing by looking at that video and then add what you need to add. Sometimes, and in fact, for many of you, that meant adding details. Many people simply did not explain enough. You said, okay, I'm gonna do, for vetting, each block must be vetted. No, how are you going to do that? What consensus algorithm are you going to use? And even within proof of work, that is a type of algorithm, it's not a specific one. So you rather should have said, I will use this particular proof of work algorithm. I think Prof. Van der Haar shows an example of Hashcash and how that's done, which is the one that I discussed that's used by blockchain. All right. What chapters from the textbook will help with the assignment? Tomorrow's, we're doing trees. All right. I will stop it there.